Now, hi and welcome back to a new episode of Code Savvy. Now, today's video is on a special request whereby some of my friends had requested that I do a demo on what embeddings and vector databases is all about. So I'll try to explain what this is all about in theory, and later in the later part of the video, I'll also be doing a demo. So without much ado, let's get rolling. Now, let us have a very high level view about what embeddings is all about, right? So, imagine that the user asks a question to ChatGPT, which is, what is a word for the pleasant smell that frequently accompanies the first rain after a long period of warm, dry weather? And the user has also uploaded a relevant PDF to ChatGPT and he or she would be expecting ChatGPT to respond based on that uploaded document. Now, what would happen here is that when a user uploads a PDF, all that text would be extracted and it would be divided into chunks. And a summary of each chunk would be stored. So it's not the chunk per se that would be stored, it is a summary of the chunk that would be stored. And later, when that user asks the question, which is essentially this, what is the word for the pleasant smell? Uh, then what would happen is that the chunk of text most relevant to that user's question would need to be fetched from the vector database, and that plus the user's query would be uh, compressed and sent as a question to ChatGPT, which would then respond accordingly, if that makes sense. So you would have your user questions, you would have your embedded chunk, the most relevant embedded chunk, extract both of those, compress it together, and send it to ChatGPT, which would process and send back the response. Now let us try to understand what embeddings is all about. So embeddings is an array of numbers that describe the absolute fundamental essence of what some text is about. So suppose the text that we are interested in is, hooray, it is the weekend, right? And if you were to ask someone to gauge the qualities that are in the sentence, it could be excitement, and it probably might be happiness, and might be something else as well, based on who is actually gauging the qualities there. So you can think of embeddings as trying to extract those qualities and converting it into numerical floating point values. Uh, and in an embedding, we would have values between -1 and 1, which represent the extremes of each quality. So if you take happiness as a quality, -1 might represent absolute despondence and sadness, whereas 1 might represent ecstatic happiness there. And if you take fear as another example, -1 might represent something being absolutely terrifying, whereas 1 might represent the culmination or apex of bravery. So in this example, zero point 0.7 might represent how happy or not the text is. Minus zero point 0.4 might represent how much the text is talking about barking dogs, which it absolutely is not. But this is just an example, right? So and another score might actually represent whether the text is talking about the pretty girl who lives next door. Uh, but you get the idea. And this array, each array would be exactly 1536 numbers long for the encoding scheme that we will be using. So there will be other encoding schemes which have a different lengths, but for the encoding scheme that we will be using, I'll be demoing, it is 1536 numbers long. I'll also be showing encoding which is lesser in number. That would be an open source encoding from Hugging Face. But primarily I'll be focusing on this embedding. Now, as most of you would already have guessed, a vector store is nothing but a storage space for all the embeddings for the different chunks there. Now let us try to understand how all of this would work together holistically. That is, you have a text which from which you'll be creating some embeddings and which you'll be storing it into a vector database. So think you have a text called facts.txt, which has some interesting facts about the English languages. For this demo purposes, I have just mentioned 5 of them. there. So the word alphabet is in ancient Greek. Set has the most definition of any English word. So essentially some interesting facts about the English languages. Now, when we generate the embeddings, what would happen is that we would split this text into separate chunks. So you can think of chunk one being the first sentence, the chunk 2 being the second sentence or the para, chunk 3 being the third sentence, and so on. So you have 5 different chunks there. You would have a embedding creation algorithm into which you will feed these chunks there. And what this embedding creation algorithm would do is it would essentially calculate the embeddings for each chunk, and it would describe the raw essence of what each chunk is all about, right? And the result of those embedding of that embedding creation algorithm is that you get those embeddings, which is like we saw previously, it is nothing but an array of numbers, floating point numbers ranging from -1 to 1. So you would have this different arrays, which you would then be storing into your vector store or database, which is a specialized database that is used for storing the embeddings there. Now, to understand a little more in detail on how all of this works is that suppose the user's question is, what is a word for the pleasant smell that frequently accompanies the first rain after a long period of warm dry weather? The answer obviously is petrichor, but we're not going into what we know. What we are trying to do here is what would ChatGPT respond if we uploaded a relevant file to it based on the question that I am asking it, right? So this is my user question. And before I ask that question, what I would be doing is I would upload a text, the relevant text into the vector database. And while uploading it, my program would break it into chunks. It would go through the embedding creation algorithm, and the vector store would already have those embeddings for each chunk of that was created out of the uploaded text there. So when I ask my question, what would happen is in the background is that the vector store would be searched for the most super relevant chunk pertaining to the question that I have asked. So there will be a search done on the vector store, and it would return the most super relevant chunk from my vector store. And that super relevant chunk plus my question, which is essentially what is the word for the pleasant smell that frequently accompanies the first rain after a long period of warm, dry weather, that is what is sent together in the prompt to Chat GPT. Now, there are many different types of vector stores, and these are just a few. So you have PG Vector, you have Pinecone, you have Chroma, you have Deep Lake, BB8, Redis, quite a few out there. What we will be using in our demo today is the Chroma vector store. You could try it out with other vector stores such as Pinecone. So feel free to experiment and learn. But for our specific demo, we'll be using Chroma, which we would be installing on our local machine. So there's no need for you to create an account or anything for Chroma, and that is why I have chosen Chroma there. Now, regarding the models, as I had mentioned a few minutes earlier, we would be using the OpenAI embedding algorithm, which has 1,536 dimensions. So this essentially means that the array that we'll be generating will be 1,536 dimensions long for each chunk there. Now, later in the video, I'll also demo the sentence transformer, which is an open source transformer from Hugging Face, and it runs locally. You don't need OpenAI for that, and but that has only 768 dimensions, which is way less than the 1,536 dimensions offered by OpenAI there. And with that, I think we are ready to see some live demos in action there. So let's go to it. Now let me go to my code editor. I am using Code Insider, by the way, Visual Code Insiders, by the way. Right? But feel free to choose whichever IDE that suits you. So inside my project, I have the facts.txt file, which essentially contains some interesting facts. I think there are around 120 facts. Let me see. Yeah, there are 120 facts there. I have different iterations of my main program. So, but don't worry, the file that I'll be sharing you should be seeing the link somewhere below right now, and I'll also be sharing it in the description there. But in the file that I'll be sharing, you'll just have the condensed final version there. So don't worry about the naming conventions that I'm used. Just try to follow on what the program is all about here. And I will have my pip file where I'll be defining all my dependencies, my library version. So I'm using all the latest library versions. As you can see, I'm using LangChain as my framework for generating this embeddings and actually storing it into vector DB when we get to that point later in the video. The Python version that I'm using is 3.11, so I'm not using the latest Python version because I found that the LangChain framework doesn't particularly work well with the later versions of Python, but you're welcome to try, and if it works for you, great. Uh, and let me now go to the main underscore 3.py, which in your case will be the main.py file there. And just quickly running over, I'll be loading the API keys from uh, my .env file, which currently is in my root project folder, but in your case I'll be just putting it in the folder in which this file would be there. So you can just copy paste your API key into the relevant section there. And if you do not know how to create your open API key, what you can do is you could just go over to platform.openai.com. That should bring you to your essentially your playground prompt, from where you can go to your settings, and there you would see something called API keys. You can either generate it from this section, or if you go a little below, you will also have your project API keys. So you could generate it from there as well. So just generate a new API key and copy paste it and keep it safely, because you won't be able to see it again there. And as I've also mentioned numerous times before in previous videos, you would also need some credits for your API key to actually work. So you can go to your billing and add some credits there. And as you can see, I have $9.74 credit balance remaining, and I topped up for $10 long time ago. So you can just do with $5, which I think is the bare minimum that you can add, and it should do you just fine, and it will last you a long time there. Right, so let's go back to the code there. So after loading my keys there, I'd be generating the embedding object. And then just to demo how these embeddings are created through OpenAI API, I've just given a sample text, which is this is the sample text for embedding, and I'll be generating the embeddings for that sample text, and I'll just print it out on the console there. And for the actual embedding, what that I want from the facts.txt file, I'm defining a text splitter where I'm defining what should be the separator, what should be the chunk size. So I'm saying it should be 200 characters. Each chunk size should have 200 characters. You can, which is an ideal size. I think you can change it based on your requirement. Your chunk overlap. So if it's 0, it essentially means there should be no overlap between the consecutive chunks. So you can play around with these values. And then I'm giving the actual text I want to load, which is the facts.txt. Since I'm using I've kept it in my project directory, I just mentioned the file name. If it is somewhere else, you would need to mention the actual path of the file there. And essentially, I'm calling the load and split function of the loader to load and split and create the embeddings there. And then I'm storing it to the docs object, and then I'll iterate the docs object, and then I'll print the content of each page, and we'll see, and ideally we should see the chunks being generated. So let's try to run this program and see what we get. So I'll go and do a new terminal. Okay, and I'll go to my project directory. I'll start my virtual environment for Python. Okay. I'll do my install based on my pip file. Since I've already run this multiple times before, it will not install anything new, but for you, you should see some things installing. If you're doing it for the first time, make sure you do not have any errors and everything is fine and everything is installed. And then I just do a Python, right? And my file is main_3.py, and let me run it. And let me increase my screen state so you can see what is being generated here. And you can see it has run successfully, and if I scroll up, you can see the different chunks being generated, and you can see the embeddings of the sample text that we had given, right? So this embeddings that you see is belong to this sample text that I've just highlighted here. This is a sample text for embedding, and it would have all the embeddings that it generated just for that single text. So you can see that is how many embeddings it has created, an array of floating numbers, right? Quite a few just for one chunk. So you can imagine when you actually upload a whole document, a large document, the enormous number of embeddings that will be created there. And below you have your actual chunks being generated from or being extracted from the document object. So this part here, right, for docs in docs, where we print the content of each chunk there. So essentially our text was broken down into chunks of 200 characters size, and this is the contents of those different chunks that you see here, right? So all of them are available. Now let us also try using the OpenAI, sorry, the Hugging Face embeddings, which is actually much lesser in number than our uh, OpenAI embeddings. So just to refer back to what I'm trying to say here is we will be using the sentence transformer embeddings, which runs locally and which will have 768 dimensions. In the demo that just concluded, we used the OpenAI embeddings, which has 1,536 dimensions, right? So we'll be doing it with a lesser number, but this is essentially we'll be using the sentence transformer, which runs locally, which is open source and which is free. So you don't need a API key, or even if you needed, it would actually be free. So there's no need for you to spend any money if you just wanted to see how all of this works. And the program is very much similar, right? So since you don't need any API keys, I've just committed out that section there. And in the embeddings, I'll be using the Hugging Face embeddings, and the model name that I'll be using is the sentence transformers that I just showed in the PPT just a minute ago. And uh, the keyword arguments, I would be using my CPU because I'm running it locally. If you have AI enabled GPU, you could use that, and you could use CUDA if you have GPU which supports AI. In my case, since I don't have, I'm just using my CPU capabilities there. Uh, and the other things basically remain more or less the same, where I'm just creating the embeddings, sample embeddings for a sample text there. I am loading the facts.txt file, and I'm printing out the embeddings there. So essentially all the other things remain the same. Now let's try running this. Okay, so what I'll do is I'll close this terminal because I want to create a new virtual environment. I don't want the same environment. And I'll again go to my project folder. I'll start a new virtual environment. Yeah, I don't need to run pip in env install each time, but since this is a demo and uh, you guys will most probably need to run it each time, I'm just doing that step there. And let me run the main underscore 4.py, which uses the uh, open sentence transformers model, okay, to generate the embeddings. Let's see what happens. Since it's running locally, you will immediately notice that it takes more time. But in the end, it generated the embeddings there. So it's segregated it into different chunks, which you can see on the console. If I scroll up, I should have the 768 different embeddings. Yes, and I do have that, right, for the sample text that we had, which is this is the sample text for embedding. And you can see the different values that has been generated, the different embeddings that have been generated, right? So how cool is that? Now, before we go any further, let us understand a little more about vectors and how they are generated. So what we'll do here is we'll do a very simple exercise on which we will be generating two vectors based on two qualities there. So the exercise, in this exercise, we'll give some scores or points to how much a sentence talks about two different things, and the two different things or qualities that I have selected is happiness and bravery. So there'll be one score for happiness and there'll be one score for bravery. And these two different things, happiness and braveries, they can be considered as two vectors in a sentence, or you can consider it as two dimensions. Now, remember, a sentence can have many dimensions, but we are just talking about two dimensions so that you understand and appreciate what a vector is all about. Okay, now let us see what the sentence is all about. Okay, so for the sentence, so I have three different sentences here, and I'm scoring it based on how happy the sentence is and how much the sentence talks about bravery. So the two qualities of vectors is happiness and bravery there. Now the first sentence is for the speech competition. The joyous child bravely went on stage when her name was called out and gave an enthusiastic speech. Now, if you were to ask me to score this sentence based on happiness, where -1 being sad, okay, very sad, and one being very happy, I would say in this sentence the child is very happy. So I would give it a score of 1, and that's why I put 1 here, right? And if you would ask me to measure it on the scale of bravery, where 1 is brave, -1 is terrified, fearful, I would again give it a score of 1, because essentially the child is excited, the child is joyous, she is very enthusiastic about giving the speech on stage. So the score essentially is 1 1, and the embedding generated or I'm giving it would be uh, 1 1, right? Now let us have a variation on the sentence on the second one, where I'm saying for the speech competition, the timid child went on stage when her name was called out. But once she started speaking, all her nervousness went out and she had a good time, right? So initially the child was timid, but once she started speaking, she lost all her nervousness and then she had a good time. So she did really well. So in this case, the happiness score, it would not be 1, would it? Because the child was not that happy. Being a timid child, she would have some inhibitions going on stage. So I would give it a score of probably 0.3. Not that happy, but not that sad either. And for the bravery, I would give it a score of 0.5. So my embedding generated would be zero point 0.3 and 0.5, right? And now let's have a one more variation of the speech, whereby I'm saying that for the speech competition, when her name was called out, it was the first time the timid child was on stage. Though she stuttered through the speech, she somehow managed to complete it. Now, the feeling that you'd be getting out of the sentence is that child is not at all happy. The child was terrified, intimidated by the audience, but somehow she managed to complete the speech there, right? So on a happiness score, I would give it 0. It's not that she was very sad, but she was definitely not happy, so 0. And she was definitely terrified there. So on a bravery score, I would give it a score of -1. And based on that, the embedding would be uh, so that's not -1 0, that should be 0 -1. Okay, so that's the score, that's the embedding that is generated for the third sentence. So based on the variations, okay, based on just two qualities, happiness and bravery, you can see the embedding values has actually changed there, right? And this is how embeddings are calculated based on various qualities that we want to measure in a sentence there. And remember uh, that embedding is a list between -1 and 1, and real embeddings, they can have more than 700 to 1500 dimensions or vectors or qualities that they store. So we're just using two. Now that we understand how these embeddings are generated, we also need to understand how the system can actually tell how similar a sentence is to one another, right? So the system should have a way, or the AI agent should have a way to know how similar something is from the one chunk is how different is it from the other. So remember, we are storing all of this in a vector database. So there would be sentences which are repeated. There would be sentences which are very similar to each other. And when we ask a question and want something to be extracted, the super relevant chunk to be extracted out of the vector database, the system should have a way of knowing that, say, these three sentences, for example, are very similar, so I don't need to extract all the three. I'll just extract the most relevant chunk out of it, right? And essentially, the three sentences might, if they are very similar, it actually means the same thing. So I just need to extract one out of it. So the system needs a way of knowing how similar the sentences are for each other, and that's the only way it can extract the most relevant chunk out of the vector database and send it to OpenAI or your relevant AI agent for processing that, right? And the way the similarity is measured is using some, again, it would use some algorithms. There are different algorithms that it can use. So I'll just mention two of them, right? So one of them is the Euclidean distance, and the other is the cosine similarity that we will be seeing here. Now let me try to explain what is the Euclidean distance. So for the three sentences that we had seen a minute back, let us give it a color code. So for the first sentence where the child is very happy and very brave, I'll give it a color code of green. For the second sentence where the child was a little timid but essentially did a great job, I would give it a color code of blue. And on the third sentence, which has a overall negative shade where the child was very timid, was terrified, I would give it a shade of yellow. Now I generated the embeddings 1, 1, 0.3 and zero point 0.5, -1 and 0 respectively for each of these sentences. Now if I plot it around the x and y coordinates of a graph, uh, what I'll essentially get is I'll get a green circle which represents 1, 1, and which correlates to the first sentence. I'll have a blue dot, right, which correlates to the second sentence and which represents the vectors -3 and -0.5 on the graph. And also have a, finally, I'll also have a yellow coordinate, which essentially represents -1 and 0 on the graph. So this should be Yeah, I changed it previously, right? So let me again change it. It should be 0 minus 1. Okay, so this point here on the graph, 0 minus 1. So I plot all these three coordinates on the graph there. Okay, and what Euclidean distance is all about is how far is each of these three sentences in relation to the sentence that I want extracted. So, for example, if I want to compare the similarity of the first sentence with the remaining two, what I would need to do is I would need to measure the distance of the second sentence to the first sentence. So essentially the distance of the blue dot uh, to the green dot, and the distance of the third point, which is the third sentence, to the first sentence, which is the green dot, and you'll get two distances, right? You'll get distance A1 and A2. Here, obviously, the distance A1 is greater than A2. Now, what this essentially means is that the sentence, which the distance of the yellow point, which is the third sentence, to the green point is much greater than the distance of the blue point to the green point, which essentially means that the yellow sentence is much more different to the green sentence than the blue sentence. So blue sentence is more similar to the green sentence. And similarly, if you think about cosine similarity, instead of distance, what it measures is the difference of angles. So if you see, for the three different sentences, if you measure the difference of angles between this sentence compared to the sentence you want compared, which is the first sentence, you will see that angle A1, which is the distance of the yellow, the third sentence, to the first sentence, is much more than the angle A2, which is the distance, which is the angle of the second sentence as compared to the first sentence. So obviously, the blue sentence, the blue dot which represents this blue sentence, the second sentence here is much more similar to the first sentence, which is represented by the green. Now, be aware that Euclidean distance and cosine similarity are just two of the different methods out of the numerous methods that are available out there, uh, which can be used to measure how similar a sentence or how different a sentence is from one sentence or the other. Okay, so just bear that in mind. Now, before we just move to the code, quickly, as I mentioned, I'll be using the LangChain framework. I am using the LangChain framework, and the LangChain framework have these classes called loaders, which you would have noticed in the, so we use the text loader. You would have noticed it in the previous demo. So for the text, you would have the text loader. For the PDF, you would have the PyPDF loader. JSON, you would have the JSON loader. You would have also for .md files, you could have an unstructured markdown loader. You could also have an S3 loader. So there are n number of loaders that are available in the LangChain framework to load data from different classes there. And how the text loader, the one that we've used in our demo, works is that it would take the text, okay, and it would split it into a page content and the actual metadata. So that is the result of loading the file, which is called the document. So if you remember, we use the document object to actually store this different chunks there, and we iterated over the document object to print out those chunks in the console there. And as the name suggests, page content contains content about what the actual content of the file is, and the metadata is info about where that document came about. And now let's move to another demo to see all of this working, how we can actually load a text document, generate the embeddings and push it into a vector DB, which is Chroma in our case. Now let's have a quick walkthrough of the project that we are trying to demo. So I'm inside my facts underscore 3 dot directory. In our case, it would just be facts there. And I have my main underscore uh, main underscore 1 dot py file. And this file essentially loads the facts.txt file, passes it and loads it into the Chroma DB. Now the Chroma DB itself is something that I have mentioned as a dependency in the pip.file there. Okay, you can see that there. So the main dot underscore 1.py file, what it contains that it loads the environment variables which contains the API key, the open API key in my .env file that I mentioned before. Um, and all the other things I think remain pretty much the same. The only difference being here is this chunk here, okay, where I would be creating my database object and you'll be using Chroma to do that. So this is all you need to do to actually push those document chunks into Chroma. And then I'll be doing a similarity search, okay, on what I want to do. So what I would be wanting to do is I want to know what's an interesting fact about the English language based on the facts.txt document that I uploaded into the Chroma vector store. So that is what I'm interested in. And hopefully what uh, this program should do is it should upload the file into it should create the different chunks first, create the embeddings, upload the embeddings into Chroma DB. It should do a search on the Chroma DB, do a similarity search, and bring back similar sentences which contain the interesting fact about the English language, right? So out of the 120 different sentences or chunks that we uploaded into Chroma DB, it would iterate through all of those and retrieve a set of matching similar sentences there, and I'll be printing those sentences out onto the prompts there. So that is my first program. My second program on the same folder is the prompt underscore 1.py. Now what this is, it is this where I'm defining my question answer process there. uh, so very similar, where I'll be loading my keys there. I'll be using the LangChain framework, and I'll be creating the Chroma database object because I want to load what is there in the database. I'll be retrieving the documents from Chrome RDB, and what I will do is and you can see that while retrieving I have some parameters mentioned here. You can play around with this. What is the chain type? Verbose equal to true, because I want to see how the chain actually works in the console. It will print out way more detail than is actually required, but it is a good way of trying to understand what happens beyond the scenes. So I've kept it there, and I'm using the LLM chat function. And essentially what I'll be doing is I'll be sending this to chat AI, right? So remember, my first program is all about loading it into the Chroma vector store and extracting the similar sentences out of the Chroma vector DB. My second program, prompt underscore 1.py, is all about taking those sentences, those similar sentences, and sending it to chat GPT, okay, to get a response. And I have my error handling and everything defined there, so feel free to go through it. Now let's try running this program and let's see what output we get. So I'll open my terminal. Yeah, my folder is facts underscore 3. Okay, I'll start my virtual environment. Good. Now, in your case, you need to do a pip-env install. I'm not going to do that because I've done it many times here. I'll just directly run the program. Okay, so I'll run my first program, which is main underscore one dot py. And before I run it, if you see, I have something called an embed folder, EMB folder here. I'll delete this folder because this is auto generated each time I run this program there. So I'll just delete this. Okay, and this is to do with where the Chroma database actually stores those. It says created, so it is created locally on my machine there, as I mentioned. So I see I've just deleted this, and you should see it being auto-generated once I run this program here. Okay, let's try it. You can ignore this telemetry event, doesn't matter. And if you look into the before you actually look into what is generated in the prompt, just see that EMB folder directory that we had deleted is now auto created, and you can see the chroma.sql3 file also being generated. So this contains our actual embeddings there, and you can see that the different embeddings similar sentences, actually not the actual embeddings there, because that is what we're trying to do, isn't it? If you remember what we're trying to do, we're trying to, let me go to the program there. We're trying to do a similarity search there, right? So out of all the embeddings that were pushed into the vector DB, we want similar sentences that correlate to this sentence. What's an interesting fact about the English language to be pulled out of the vector database there. And you can see it has pulled out around probably uh, 10 or 12 sentences out of the 120 sentences. So now this might not actually make sense that these are actual facts about the English language, but it is just that when it calculated those vectors, these vector values for all of these sentences were similar, and it extracted all those similar sentences out of those vector database. Okay, and now let me run the second program, which is essentially we would be sending these similar sentences that we extracted using the similarity search and sending it to uh, chat GPT, OpenAI's chat GPT, to get the final answer about what is an interesting fact about the English language. Okay, let's try running that. And that would be Python. Python prompt underscore one dot py. Okay. Hmm. Okay, and we have got the final answer. You can see the final answer, right? An interesting fact about the English language is the word dreamt. It is only English word that ends with the letter empty. So you have got that final answer you wanted, which is what is an interesting fact about the English language there. And you can see how the chain works in the background, the number of input tokens it took, the number of output tokens, the type of AI, the model that it used. Because we used verbose output, you can see all those details in the output. You might have some warning errors and some minor deprecation warnings. Just ignore it. But essentially, our program worked, and you were able to see the final output. And again, just to recap on what we did here, you have two programs here. You have your main .py program, which essentially takes your text document facts.txt, breaks it up into different chunks and creates those embeddings and then pushes it into the Chroma vector DB. From the Chroma vector DB, we would be doing a similarity search based on a sentence we provide, which is what is an interesting fact about the English languages, and it would return some chunks from that vector DB, a subset of what we actually uploaded into the vector DB. And in the second program, which is prompt.py, we would be using that subset that we retrieved using the similarity search, and we'll be sending it across to ChatGPT to get the final answer about what's an interesting fact about the English language. And this is the final answer that we get, that dreamt is the only word in the English language that ends with the letter MT, which is an interesting fact, by the way. Now, before we go on, let us quickly also try to understand about the redundancy filter and why we require it. Right. So imagine that you have text that you have uploaded that contains duplicate sentences. So if you look into this example which I'm showing on screen, you might have the facts.txt whereby the same sentence has been repeated. So you see the first sentence, the word alphabet is ancient Greek, and it goes on to describe what it is about. It has been repeated twice. The second sentence, which is the set, has the most definition of any English word language, has been repeated here, and it has also been repeated here. So essentially, you could have duplicates there. Now, if you do not have a redundancy filter, what you would be doing is you would be skewing the results that you actually push into your vector database there, right? So you would have skewed results out of what actually is generated there. So you would need some sort of redundancy filter which would take away those duplicates there and just load that relevant sections into your vector database, so that uh, it's easier for your program to actually extract similar kind of sentences based on what you have asked. Otherwise, it might actually extract the same sentences n number of times. So if you did not have those redundancy filter, what would happen in our previous cases, if you uploaded the same sentences in your facts.txt file, and which were relevant to the question that you asked, it would extract those same sentences, say 10 or 12 times, which did not sort of make sense, right? So you would need different kind of sentences, different sentences which are similar to what you have asked, and that is what you need to send to ChatGPT. So for that, what we'd be doing is we would be using something called an embeddings redundant filter, which is essentially nothing but it would just eliminate those duplicates there. So if you look into this case, once you use your embeddings redundant filter, this whole chunk actually just has two sentences, right? Because all the other are duplicates. It would have the first sentence, which is the word alphabet is ancient Greek, and the second sentence, which is set as the most definition of any English word. Now let us see this in action. Now I am under my facts underscore 5 directory, where I have created a new class called redundant underscore filter underscore retriever dot py. So this is a custom retriever that filters out redundant documents, and it uses the maximum marginal relevance, which is the MMR relevance there. Uh, Now, don't worry about these technical terms. Just understand that this is a method by which you can eliminate this redundant documents within your files that you're trying to upload there. Okay, and there are other methods by which you can do it, but I'm using the MMR method there, and it is relevant to the query vector, and the code is nicely commented. Just go through it and you have various options, like you have your lambda underscore mult, which controls your diversity. So higher values, it favors the relevance to the queries, whereas lower values, it favors diversity among relevance. So I've created this class called the redundant filter retriever, and I'll be using it in my prompt underscore one dot py file. Uh, so this chunk of code here, right? So I'm using a custom retriever that reduces the redundancy in search results, and I'm passing my embeddings to the retriever there, and I'm passing the Chroma vector DB. That is the only major change that I'm doing here. Others are pretty much exactly the same as we saw before there. All right, so there's not much difference there. Now let me try running it, and you will not see any difference in the output results, because the text that I'm uploading does not contain duplicates. But if you had duplicates, this would be useful, and if you run it, you should hopefully see the same results. So let's quickly try running it. Okay, so I'm under facts underscore 5. Okay, Now let me start my virtual environment. Again, if you're doing it for the first time, please do run pipenv space install after this command. If not, you can directly run the files. So I'm doing the Python main 1.py. Yeah, I have my similar sentences being extracted out of the vector database, and let me run my prompt.py. Ah, yeah, and you see the exact same results there, isn't it? So there's nothing different there. Interesting fact, the word dreamt is the one that ends in empty. The exact same results, but will be useful in cases your document contains duplicates there. Now, before we wrap up, if you wanted, you could install the Jupyter Notebook and you could write some code to actually illustrate on how the different values of the vectors there. So what I've done is here is in one of the cells of the Jupyter Notebook. So I've named it scores dot ipynb. Uh, I have put in the three different sentences that we used on the one of our exercises there. So if you remember, we used three sentences which and we used two qualities, joy and fear, and we measured those qualities and we created the cosine and the Euclidean distance graphs for these sentences to see how similar they were with each other. And I've just copy pasted those three sentences, which is about the speech competition and how joyous the child was for the first sentence, and how she did an excellent job, though she was timid in the second sentence, and in the third sentence, how the child was actually quite terrified there. I've given the qualities of joy and fear. And when I run the Jupyter Notebook, okay, it should generate a graph, an illustration. So you can see that it is running, and you can see that it has generated an illustrative representation of the two vectors that we have used, which is joy and fear. Now the sentence are all rabbled up because it doesn't have any space, but you get the general gist of what this is trying to do. Now this is just an addendum to the whole demo, and I just thought it would be something fun to add at the end, but it's really optional. So if you do not want it, just ignore this part there. And with this, I've come to the end of my video. Hope you really enjoyed it, and it would really give me more encouragement if you liked and subscribed, and it will also help these videos reaching a larger community where I hope to find it helpful for somebody trying to learn new things. So till we meet again, adios.